We all good over there? Do I still have you, CC? Nope. She's gone. Oh, no, you are there. Good. So I turned on the streaming. Hopefully it's coming through soon. I've got one viewer. That must be you. Good morning, everybody. We're just going to sit tight for another 5 minutes. I'm going to give myself an extra 5 minutes to get the stream sorted first. Now, Cecilia needs to put in headphones because I can hear myself coming back at myself. And it comes back like 5 seconds later, so it's really surreal. You've just finished saying something and then it comes back. I'm amazed at how good the lag is, though. It's there, but given what's going on, the amount of data that's being sent all over the damn place. None of this goes to Echo. We can't put this stuff on Echo because it doesn't have the capability. Can't do, I mean, Echo 360 can, but it doesn't work from my house. And a lot of other classes are able to put things on Echo via Zoom, but Zoom has a 300-person limit, so it's no good for us. Because we still have 1,200 students enrolled in the course. 4 times as many as Zoom can cope with if everybody turns up. Well, now's the time to hit me up if you've got any loops things you want me to cover in particular. We've got about an hour, I suppose, to talk about more advanced loop stuff. I've got ideas. You can see I've got one of them open right now, the logic tables. I'm just trying to think of a nice example that might allow us to experiment with the logic tables a bit more. And why they're called logic tables. Which is not a name I love, but it's a name I can cope with. Oh, there was one question that I've picked up on might be useful to talk about, which is the difference between the statements inside a for loop and the update statement. More circles, circles everywhere. circles. Okay. Yeah, that's what we're interested in. And that's the circle diameter. All right, I like that example. That might be the one we do for nested loops, I think. My phone just won't. So yeah, so this is the question. Can you use multiple initializations and update statements? So that's something we'll experiment with to find out. Because that's how you do these things often. Programming languages have so many rules, it's hard to remember them all. You often just experiment to find out. And maybe look at the documentation and combine those two things. Okay. What do I use? This is just a basic OBS setup on my computer, which doesn't seem to cause me too much trouble. The main thing that's good about OBS is that it's, from my point of view, is that it seems to have some sensible microphone defaults so that you can actually hear me. Everything else I set up, I mean, are way too low or way too high. And this is a terrible mic, but it's getting the job done just. My good mic disappeared. I haven't had a chance to get it back. Just going to try and get my phone not to turn itself off all the time. Yeah, so consultation hours, I'm not sure what to do about them. I didn't have any makeup ones scheduled, but I might have to because there's quite a lot of stuff going on. It'll come out on announcements if I do. I think we should get going. Okay, so I haven't quite got the watching the comments thing sorted yet, so I'm definitely relying on my voice in my head to pass on as many as possible. Okay, loops part 2. So what on earth might we talk about in loops part 2, because we did everything in loops part 1? Just like every other topic with software, there's not a lot to it. There's a few basic rules and you follow them and everything expands from there. If you can do those basic things, you have just, it's hard to explain. It's like Lego, right? It's just a few basic bits and you can put them together in a bazillion different ways. But there's the edge cases and there's the complicated combinations. So that's what we think about here. The complicated combinations of the continuing condition on the loop and the complicated combinations of loops with loops is what I want to talk about today. So let's address that issue that has come up about what to do with these initializers. So I'm going to get a program up and running to start with. You can see I've got a example one here to inspire me, but let's go again. Never hurts just to remind ourselves of what avoid setup and avoid draw does. And 800, 800 as always. And a background of 0 and no stroke and fill of 255, my preferred choices. So all I'm going to do with this one, just as always, you probably noticed every second program starts in exactly the same way. Width divided by 2, it's just a circle in the middle. Because from that we can build so much. And we always start off with that and run it to see that I got my colors right. There we go. What I'm going to do here is I'm going to switch from fill, no stroke and fill to no fill and stroke because I need to draw circles on top of each other this time. So that will go no fill and that will go stroke. And when I run that, hopefully I just see an outline of an ellipse because that's what that does. Very good for a circle. What I want to do is make those circles bigger and bigger. So not just have one in the middle, but have multiple of them. So I'm just going over a bit of stuff that I covered last time here to warm us up. So if I did a slightly bigger ellipse after this one, it would look, if I wanted it to sit in the same spot, that's exactly what I would do, use the same spot, but I would make it bigger. And because there's no fill, that's okay. It'll go drawn over the top of the other one, but with no fill, you'll still be able to see the one inside. And this is a way that I can draw a kind of target shape or concentric circles. And I like that as an example of loops because if I'm not using loops, I have to do multiple of these ellipse lines and it gets ugly fast. So I can keep making these bigger, no problems. And 320. Yeah, easy. And that gives me a bunch of circles, but I'm restricted to how many circles I could do, how big they are, and changes are quite difficult. Whereas if I get myself a loop to deal with that thing that was happening over and over again here, and notice it's the thing that's happening over and over again within one draw algorithm, not something that's happening over and over again because the draw algorithm is going over and over again. I can do this with a loop. So we were talking about while loops before, and with a while loop, it looked like an if. You did a condition and a body, and that was really all there was to it. But to make this condition work, you had to normally bring in another variable, because normally if I just put a condition in here, that condition will be true once, right? But unless something changes, it'll just constantly be true, and I'll end up in an infinite loop. Or it'll be false, and unless something changes, it'll just always be false. So it's much less useful just to try and use things from the environment to do my condition, because it's unlikely to change while the program, in the middle of a draw. So, and I need things that are going to change in the middle of a draw. So I create myself a variable, maybe that's helping me keep track of something, and that does change in the middle of my draw so that so the condition can go from true to false. And let's make this one a sensible thing to do might be the size of the circle that I'm currently drawing, because the first circle I drew was at 80, right? And then the second circle I drew was at 160. I might say, look, as long as size is less than or equal to 320, keep going around this loop. And certainly that's going to happen at the start because I just set size to 80. And I say the thing I want you to do in the body of the loop is draw the ellipse. Now, that's not enough. First of all, that would just draw ellipses size 80 over and over and over and over again. Not what I want. I want ellipses that grow. And so something that changes as this loop goes around is exactly probably this variable size. It's not changing yet. I've gotten myself in a knot, so we'll stop, think about what we have here. We've introduced a variable size 80. We've said that as long as size is less than 320, which it definitely is at the start, draw me an ellipse 80-80. Cool. And because what we know about loops is when you get to the end here, it goes back and tries the condition again. That condition comes up true, and it just runs again, draws another ellipse at 80-80, and so on and so forth. So you might be tempted to think that this program, if you run it, will just draw a single circle at 80, or in fact draw many, many circles at 80 over and over and over and over again. But when you run this program, it will do nothing. And the reason it does nothing is that you've got to remember the cycle of processing programs. And I'm going to draw it on my little screen here that hopefully works. So you've got to remember that with a processing program, we always run the setup function once. Then we run the draw out function or algorithm, right? And it goes from the top of the draw all the way to the bottom and it finishes. So whatever code was in here has to run all the way to the bottom of the draw. And at this point, a little picture comes out onto the screen. But nothing happens while we're in the middle there, because remember that the operating system here, this is processing over here, and this is the operating system over here. Processing finishes the draw and says to the operating system, please spit this out on the screen for me so the person can see it. And then draw goes again from the top to the bottom, all the code gets run top to bottom, and then the new picture gets drawn out on the screen. So maybe the person's running away. Now what's happening with this code is that inside the draw function is this while loop. And it's a while loop that's never finishing. So it's coming into the while loop, going to the bottom, drawing one ellipse, coming back around, drawing another ellipse, coming back around, drawing another ellipse, coming back around, drawing another ellipse, coming back around. Doing this forever. So it never ever gets to this bottom point where the thing appears on the screen. So we have a program that's running forever and doing nothing, which is why we just get the gray background, because it never got to the end of the first draw algorithm, so it never got anything to put on the screen. So that's one tip I wanted to point out, the strange behavior you get from what we call infinite loops. So the problem is that we have an infinite loop here, and I'm sure you can all see why. We have an infinite loop here because I never changed the size variable that I was using to work out how long to go for. It started at 80 and it stayed at 80. Much more sensible, what I really wanted was for every time around, I wanted to draw a new ellipse at a different size. So I started with 80 and then I wanted to draw 160. Well, 160 is 2 times 80. So at the end of that first run, I'll update size so that the next time around, different things happen. Different thing that happens is the condition gets checked differently because it's now 160 less than or equal to 320 instead of 80. Still comes up true and we go again. And a different thing gets drawn as long as I actually use that variable down here. So that will work an absolute treat. Almost. So I didn't quite get what I wanted here, and this is a great example. I really like this example. What's gone wrong? Compared to what I wanted. Remember before I had the 80, 160, 240, 320. Well, what's gone wrong is I've done the wrong update. I didn't really want size to double each time. I wanted size to go up by 80 each time. Just so happened that the first time around, going up by 80 was the same as doubling. So I really want that to be size equals size plus 80 to get back what I had before. And there we go. Very cool. So it's shorter and it's much more malleable, right? I can do more things with this. I can, for example, decide I don't want to start at 80. I want to start at 40. And I want to grow by 40 instead of growing by 80 each time. And if I do that, I get more tightly drawn circles. So that's a standard example of why a loop is good. But it also gives me the chance to talk about these the updates and the initializers that come from a for loop. So I'm going to do the exact same thing, almost exact same thing, with a for loop. But I'll do it with starting maybe 10 pixels off from the other one. And I equals I plus 30. So this is going to do the same thing, but 10 pixels offset from the other one. So if we run it, I'll just change the color too. Okay, so we've got the two different sets of circles all being drawn. I seem to be, oh, they're going up by 30 when I wanted them to go up by 40. Yeah, so the same set's just being offset by 10 pixels from the other ones. So it's definitely doing the same thing. I wanted to compare the two. So there are three features of the while loop that become very important in the for loop. The first feature here is called the initializer, which sits up here on line 9. It gets my variable ready so that I can use it in the condition. Then there's the actual condition, which uses that variable And it's important that it uses that variable because otherwise the loop would end up being infinite or something like that. I've got to use a variable that changes. And then the third part is that I've got the variable that changes. I've changed it at the end of the while loop. So a for loop just lets you write your loop in exactly that form every time. The initializer is the first part before the semicolon. The condition is the second part, and the update is the third part. So a lot of people have been asking, can I have multiple setups and multiple updates, multiple initializers and multiple updates? Well, you can't, because as soon as you put a semicolon here, it says, the next thing coming must be the condition. So I couldn't put 2 lines of code here, jam them in, because the semicolon doesn't mean end of code, give me the next line of code. Here it means end of code, give me the condition, please. And the same thing over here in the update. I can only put 1 line of code in here, only 1 statement. So this is where it's important for us to know the difference between expressions and statements. In here goes a single statement, in here goes a single statement, and in here goes a single Boolean expression. And that's all we can do. If we've got some program where we want to have multiple initializers and multiple updates, we can just use the while version. There's nothing to stop us putting extra lines right here or extra lines right here. We can do whatever we want. The for loop is more restrictive, but that restriction makes it more useful, easier to read, because this is such a common pattern, bang, bang, bang. It also makes it impossible to forget the update. Like you saw when I did my infinite loop, I'd left out the update, and that's much, much harder in the for loop. So you're much less likely to write the infinite algorithms. Okay. So that covers the answer to that one. I didn't actually need to experiment, because as soon as I realized, well, what would my experiment look like? It would look like, and that can't possibly work, because I know that the syntax is that has to be a condition. Okay. What next? The draw and the way loops work with draw. So we had a little bit of a look at that, but let's look at another version of it. Well, let's talk about it more deeply. So loops are things that happen over and over and over again. And the draw algorithm is something that happens over and over and over again. So how are they different? Well, in some ways they're not. Often you'll hear the draw algorithm called the draw loop, exactly because it's working like a loop. It happens, and then it happens again, and then it happens again, and then it happens again. Importantly, it's an infinite loop. So as long as the program's running, it'll just keep going. And just like we saw before, infinite loops are troublesome. So to make this work, processing says, well, look, infinite loops are troublesome. They're going to get in the way of you trying to do anything at all. But animations have to be infinite loops. That's what an animation is. It's just show me the next frame, one after the other. I mean, when you're watching a movie, you run out of tape eventually. But we're on a computer, we don't run out of tape eventually. Our animations could go forever if they wanted. So the logic of it is they've said, animation just requires an infinite draw loop. And infinite loops can be tricky, so we're going to take control of that infinite draw loop for you. We're going to put the operating system in between you and your infinite draw loop, and all you have to do is know what you want to do on each frame of the animation. You describe that for me, and I'll look after the rest. So processing is looking after the thing going on the screen. It's making sure that after each run of the loop, the draw loop, something happens on the screen, instead of what we had, which is just spinning our wheels, nothing happening. But then within the animation frame, we can put as many loops as we want. So we can still have our while loop in here. So the reason we put while loops inside draw is whenever we want to do more than one thing on an individual frame, not when we want to do more than one thing during our animation. We already did more than one thing during our animation when we just did normal animation where we had variables. But if we have to do multiple of something in one single frame, we have to use the loops. It can be easier to experiment with loops outside on a static program so that you don't have the complexity of the draw loop. And I'll show you how to do that. The trouble with the static program is that it'll only draw a single thing on the screen. I guess that's not a huge problem. So let's make a static version of this one. Remembering that a static program just runs once top to bottom and doesn't do anything else. I could, for example, take this code and drop it in as a static program. Didn't quite happen because I didn't get the size. I think I can still do those in a static program though. Sorry, what was that? And I'll put my background and my no fill and my stroke in just to make us. Now I've noticed a bit of an issue here. I'm using the size variable and size up there is the same. So I'm just going to change this to S to make sure that doesn't get in the way. There you go. So I've got a static program doing the exact same thing. And that's because this thing was just showing the same thing on every frame. So there was no benefit to having the dynamic program. But there is a difference, right? This one's drawing those concentric circles once. This one's drawing those concentric circles in one frame, then again in another, then again in another, but not showing anything different. So what would it mean to animate some concentric circles? What would you ever do if you wanted to combine the two? Well, it's if you want to animate it. What might we want to do with these concentric circles? Well, one thing we might want to do is have them expand so that it starts. I'll get rid of the second lot. Do I have a comment? Comment, uncomment, yeah. So that it starts 40 apart from each other, but then the distance apart from each other grows as the program goes on. Now remember, to do any kind of animation, anything that's going to be different from one frame to the next, you have to have a variable for it. Well, I actually already have a variable for this one. The distance between two frames here is called the size. But I was just using it inside the drawer, so I've got to move it outside the drawer to animate this guy. And when I do, so it's going to start off at 40. I do, the loop still does the same thing, but instead of going up by 40 each time, it wants to go up by size each time. Size equals size plus size. No, that's not right, is it? Because now we're using size for two different things. We're using size to keep track of the while loop, but we're also using size to keep track of how far apart they're going to be. So I actually need a second variable. I'm going to put that all back where it was and realize I need a second variable. Now I might have discovered that the hard way if I hadn't done this 1,000 times. But I want a variable that's the gap on the first frame, and then I still need that size variable to go bang, 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 bang inside the draw frame, inside that animation frame. But then the next time I come back to the animation frame, I need a new gap so that size goes bang, 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 but with different numbers. And it needs to start at gap and go up by gap. And gap needs to change every time I do an animation frame. Now I don't want to make changes to gap inside this while loop because that's all about drawing the different circles. The part about animating the circles is happening at the very end of the draw and algorithm. So here, I'm just going to do gap equals gap plus 1. Okay, there we go. And I might not have got exactly what I wanted because maybe I wanted those to keep getting bigger and bigger. But the limit I put on them at 320 stayed the same. So maybe I want to always see the exact same number, which was 8 times the gap. So now the size it has to get to before it stops drawing will also grow. And I think I will get, there they go, just constantly growing, and it goes on like that forever. So that's a combination of loops with the draw to animate something that still has to happen multiple times inside the draw. Okay. So I've been constantly using the while loops here, but in general, you'll almost always just do it with a for loop. And one of the reasons for doing it with a for loop, when is it better? So I would say 99% of the time it's better to use a for loop. You'd only use a while loop when you needed to. Most programmers will default to using a for loop, and then they'll realize they need 2 updates or 2 initializers, and they'll have to jump back to a while loop. So we're from now on probably going to try and stick to just using for loops to start to get into the habit. In particular, when we get to compound data, we'll be looping over compound data forms over and over and over and over again with the exact same type of loop, and it's going to be a for loop. So let's switch this one into a for loop. Okay, so the first thing to do is switch that keyword to a for, move that initializer into the first part, move that update into the last part, and we're done. Okay, so get used to using for loops more than while loops, but we ask you questions about both, and you can convert from one to the other, just like I did then. All you do is take the initializer and put it up the top, take the update, make it the last line of the body, because that's all that really is. That line of code there just gets literally converted by processing, stuck in the last line here between line 13 and line 14. No magic to it. So this makes it easier for me to not try that silly thing I tried before, where I tried moving size equals up to the top here, because it's obvious it belongs in the for loop here. Don't forget that int on the thing here either. You need to declare it. Okay, so we have now talked about for loops and draws and infinite loops, and things are moving along. We should have a look, I suppose, at nesting them. We crept up on this via the for loop because we just kind of did nest some loops without realizing it. Because that draw algorithm is going over and over, and then inside there we're doing a while over and over. That's a loop inside a loop. But we can actually explicitly do loops inside the draw as well. You can do them as deep as you want. So I want to remind you of the expression versus statement distinction. Remembering that expressions evaluate to something. So this expression here, size less than or equal to 8 star gap, is a Boolean, true or false. Every time you ask that question in processing, you get an answer, true or false. This thing here, size plus gap, that's an expression. Every time you ask that, you get a number back. But this thing here, size equals size plus gap, is a statement. It causes something to happen, but there's no answer for it. The answer is not 5, true, character C. It's just a thing that happens. So this one here is a statement as well. So loops are always statement, expression, statement. And in the body here is a set of statements. It's not an expression, not something that evaluates. It's a set of statements. And you can put any statement in there you want. An ellipse is obviously a statement. It makes something get drawn on the screen. But guess what? A loop all together in one hit, lines 12 to 14 considered together, that's a statement as well. It's a statement that does a heck of a lot. It's a statement that draws ellipses over and over again, but it still counts as a statement. So if the body of a loop can be any statement, and a loop itself is a statement, there's nothing to stop us from doing this. Doubling up, putting the loop in the loop. Now, the few things you'll have to do is you can't reuse the same variable name here. So I've got to go to J just to bring something else in. Not quite sure what this program's going to do. Things are going a bit shonky here. Let's run it and see. I haven't even thought about it yet. Does not much of anything. It does the same program again, but every time it's drawing way more ellipses over the top of each other. So that's why it's getting a bit slow. But this is totally legal. The thing I want to point out, and I want you to, even without thinking about this program, is to recognize what's inside each loop. There's a loop on line 13, which we're going to call the inner loop. It has one statement inside of it. The one statement is the ellipse line, but that ellipse line gets run many times. The outer loop on line 12 has one statement inside of it, but it's a complex statement. It's this guy, just the one statement. You've got to keep that straight, I think, because it helps you to work out the cycle of a nested loop. I'm going to try and turn this into something that actually does something. Let's see. So we've got a size. The size is going up every time, and we're drawing an ellipse each time. So what we're going to do as well is, instead of just drawing an ellipse, we'll draw an ellipse that's got other ellipses. I've got to do some maths to do this, but I can do that. That draws other ellipses at the four corners of this ellipse. So every time I go to draw one ellipse, I'm also going to draw the main one outside, and I'm going to draw four others inside. So the main one outside, oops, goes there. This is to show you that you can have two statements in this ellipse. So now, in this for loop. So now the outer for loop has got two statements inside it. That statement, which happens once, and this statement, which does happen once, but as it's happening, it causes many, many other things to happen. And then I'm going to make j just go from 0 to 4. Can I do that? Oh, it's going to be tricky. No, that's not quite what I want. I have to use a little bit of maths, I think. I'm trying to think of what I can do without having to bring in some trigonometry, but we're in circles, so it requires... let's go with a 4, and j goes up by 1 each time, and let's just do something. We're going to take the width divided... No. I'm having trouble coming up with an example that works for this. So I better stop and think for a sec. I might just have to use the trigonometry. Let's have a look at it, because I think the trigonometry is interesting anyway. I haven't done it in a long time, so I got to remind myself. Need more pages because my notebook doesn't have quite enough space. So if I'm drawing a circle like this, at the center, that's width divided by 2, height divided by 2, and I wanted to do another circle here, another circle here, another circle here, and here, what would be the x and y coordinate of that spot there? So that's quite, well, it's not too bad, right? It's the center plus the height. And if I wanted to know the position over there, it would be the center plus the width in the center. But what if I wanted to do more of those circles? How would I work out these ones in between? Well, I do a little bit of maths, right? Say this one here, well, let's look at this one here. I need to know that angle, and then I need to know that the x position of that guy is going to be the width plus, it's either sine or cos, and I always forget. One of you can tell me. The sine of the angle times the width, and the other one's going to be the cos of the angle plus the height. I think it's the other way around. But that also means I need to know what this angle is. And this angle is done in radians in processing. So here the angle is 0, and I believe on the way round this way we go all the way to 2 pi radians. So let's say I wanted to draw one here, here, you know, at all the different, I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different slots that I wanted to use. So the angle would start off at 2 pi on 12, well, it would start off at 0, then it would go to 2 pi on 12, then it would go to 2 pi on, well, 2 times 2 pi on 12, and so on and so forth. So I'm going to need a variable that starts at 0 and then goes to pi on 6, and then goes to 2 pi on 6, and then goes to 3 pi on 6. So I'm going to make one of those. That's what this guy is. He starts at 0, and as long as he's less than 2 star pi, Processing has a 2 pi for me, which is useful. And it doesn't go up by 1 each time. It goes up by pi divided by 6 each time. And I immediately realized that pi divided by 6 is not an integer, so I'm going to change this to a float to make it all work for me. And just to be sure, I'll put that as a 0.0. So now I can use that j. So I've now got a size variable which is keeping track of how wide this circle is. And I've got a j variable which is keeping track of how far around this circle I am. And I want to use both. So I'm using the size to just draw an ellipse first up, and I'm going to use the j to draw a bunch of these tiny ellipses around. So where does this ellipse go? Well, it goes at width divided by 2 plus, has anyone told me whether I need to use sine or cos? I'm going to go with cos. And so that's my new position. The x position is width divided by 2 plus whatever the trigonometry told me was the right thing. And the y position is height divided by 2 plus sine, whatever the trigonometry told me was the right thing. And I'm going to make these quite little. Let's make them 5, 5. And let's see if that works. So I'm hoping that this is drawing many ellipses, right? Just like the concentric circle one was. But every time it goes to draw an ellipse, a whole nother loop runs that draws ellipses around circles, really, not ellipses. Oh, score! It's back to being animated, which makes things a bit tricky to keep track of. So I'll kill the animation. All right, didn't quite get it right, did we? We're going out to too many of them, but I got the right idea. Yes, every second line is missing, so these need to be divided by 2 over here. Just got to work my maths a bit better. But now we've got a loop inside a loop. Brilliant. I like that. A loop inside a loop, because when I went to draw this first circle, I didn't just draw the circle. That was the first statement I did. But then I ran another statement, which was the inner loop, which drew 12 other circles using the trigonometry to get them on the edges. And then I changed size and jumped out and drew this second one. And it was, I drew another 12 on top of it. I'm just going to do one other trick to see if this works for me. No, we'll stick with this. So, loop inside loop. That's one reason we might want to do it, right? Here's a program. I just realized I've just drawn a cassette. Oh, so exciting. Yesterday, I got a brand new cassette for my rear wheel. You don't know what a cassette is? You don't really care? But you can look it up, mountain bike cassette. They look just like this. This must have been like some kind of subconscious thing where I ended up drawing a cassette, because I promise you I wasn't thinking about it until I saw it. All right. Circles inside circles. The next thing to think about is the order that this goes in. That's very important. So there's a lot going on in this program now. There's a draw going over and over, but that doesn't matter because this is a static program. There is one loop that's drawing each of the big circles, and then there's another loop that's drawing each of the little circles. We want to know, tracing these programs is just as important as ever. Let's trace this one. I already gave you a clue because the order in which I talked about them before is exactly the order in which they draw. The first thing to get drawn onto the buffer in this program is that first circle inside there. Now the trick I wanted to try was to gradually increase the stroke color. So stroke starts at white, and what I'm going to do is every time we do something, no, it's too hard to do that. Okay, we'll just talk about it. The very first thing to get drawn is this big circle here. Round it goes. The very next thing to get drawn is this tiny circle here. It's the circle for when size is 40 and j is 0. And the next circle that gets drawn is the one below it, if I've got my direction correct on processing, which is for when size is 30 and j is whatever pi divided by 6 is. Then the next one is that one there, because the size is still 30, but the j has gone up. Then this one, the size is still 30, but the j is now gone up to 90 degrees. Size is still 30, j's gone up, 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 size is still 30, j's gone up. Keep that on and boom. When we get all the way around to here, the j in the loop has finished its job and it stops. Then we go back to do the next outer one. Size is 60. Now I'll go this way. Just make the... Nope, that hasn't helped. I pressed the wrong button. Console, I wanted this one. Okay, so sorry, what was that? Ah, okay. Yep. Let's shrink that back down again. Okay, so let's trace this through with the actual code and understand why the statement, the fact that these are statements, leads into that. So this program runs top to bottom. It goes in at line 8, then line 9, then line 10, then line 12, which is this whole statement here. And it's just going to try and run that whole statement. But running that whole statement requires running lots of other things. So the very first thing it does to run that statement is this guy. Good. Then the next thing it does is it does this comparison. Fine. The comparison comes up true. So it goes and runs all of this. Now running all of that means running line 13, which draws the big circle. And running all of that means running the statement at line 14. The statement at line 14 is this thing. And it's going to run this to exhaustion before it tries to go anywhere else. This for loop, the flow of control doesn't pop outside this curly brace until this has finished everything it wants to do. And everything it wants to do is to start up the j at 0, check that the j is less than 2 pi, and then run its body. So it does that, draws one of the little circles. Then it goes back. It makes j go up by a little bit because that's what we told it to do. And it goes back and checks the comparison again. The comparison comes up true, so it runs another small circle. Comparison comes up true, another small circle. We don't move forward at all until this loop is finished. This loop does all of its business before it pops out at the end and says, I'm done. I just drew 12 of these circles. In fact, 13 because I made a mistake, but I drew 12 of these circles. Now I'm ready to move on. But we're still stuck into the very first run of the loop on line 12. But of course, there's nothing else to do, so it pops out of its last run and goes back round to go again and runs its entire body again. And that means updating itself with the size plus gap, running another call for a big ellipse, which makes a slightly bigger one, and then going back in and redoing that whole inner loop to exhaustion again. Okay? So one thing people often get wrong is which order are these loops happening in, but this is the only order it could logically happen in, and that's exactly what it does. Okay. Do we have any other questions? Anything I can address at this point? So one of the fun things that comes up with doing loops is that you'll often do some fancy, tricky things like I just did. Now this is I guess not that fancy or tricky, but I did have to scribble it out to work out what I was going to do. Where the way the j variable is changing is not the simplest thing in the world. It starts off at a number 0.0, easy enough. It goes up to a number 2 pi, easy enough, but how much does it go up each time? I had to think hard about it. And then how do I use it was something I had to think hard about as well. And yes, by the end of this course, you want to get to the point of being able to use these more complicated mathematical expressions inside your loops. And the reason is that a loop is very, very flexible, very, very valuable. You'll often need it and not have a choice but to use it, except that the thing you're trying to do needs the maths, like my one here. There's no other way for me to work out where these circles go. So as soon as you start trying to do interesting things, you'll find yourself dealing with loops. You'll realize that a loop is the answer, and you'll also realize that, you know, the variables that I'm using for loops, they have to go up in a pattern, a simple pattern. These are a couple of simple patterns. I don't have a lot of choices about how this one would be I plus 1, this one would be I plus 2, this one would be I plus I. I don't have a lot of choice about those patterns, so often I've got to carefully pick a series of variables that what we call what do we call it? I've lost track of the word. The I variable, the thing that's driving our loop. We have to carefully pick what the sequence of those numbers is going to be, and we have to carefully use that number to do something. So here it was a j plus pi on 6, which I guess that's not super complicated, and then it was also to use that j in the sines and the causes. But we would consider that an advanced concept that you would learn with a bit of experience and familiarity. At the start, you really just need to know the mechanics of the loops and to be able to trace the mechanics of the loops yourself. So maybe the next thing to do is think about how should I be tracing loops? So first thing to say is that you trace them just like you trace anything else, by going line by line through your code. You can see a problem with that already, I'm sure. Way too many lines. A lot of circles just got drawn. If I wanted to trace this properly, I would have to trace. I'd be going for a long time. So we create some table. We do it in a table form, which helps us to see the pattern of what's going on. So let me trace this one for you and show you what the table looks like, because this is a relatively complex one to trace. We call them logic tables, but I just think of them as tracing tables. I'll make myself a table that's keeping track of all the interesting things. And the interesting things are definitely those variables that are driving the animation, the loop. So I've got a size that's driving one loop, and I've got a j that's driving another loop, right? But the other interesting things here are the conditions in the loops. So I haven't left myself quite enough space, but this one is size less than 8 star gap. And the other condition was j less than 2 pi. Okay, so I need more columns on this table, but this is a start. And what I do is I trace through the program step by step and write out what each one of these is. So when I hit line 12, gap is 40. So when I hit line 12, size is 40. Then I hit line 13 and size is still 40. And then and j doesn't exist yet, right? Then I hit line 14 and j is 0.0. Sorry, before I do that, when I hit line 12, size got set to 40 and I checked if size was less than or equal to 8 star gap. So it can be hard for me to work out, is size less than or equal to 8 star gap, but it's much easier if I've already got the 40 over here on the left. And in fact, gap always stays 40 in this program. So I'm really checking, is 40 less than 8 times 40, which it is. And that's what allows us to go into the loop at all. And then we get that, so that's my tick for true. You can put T or F here, or tick and cross, whatever you want. Sorry about the focusing there. So now I do go inside that loop and I do run line 13 and draw that ellipse, and I do run line 14 and start the next loop, which sets j to 0. Then I'll ask myself, the next condition gets checked, and the next condition checks, is j less than or equal to 2 pi? Well, 0 is definitely less than or equal to 2 pi, so yes, I go into that loop. And I go into that loop and I draw an ellipse. So maybe over here on the right hand side of my little thing I might say, you know, ellipse drawn or something, just some notes to myself. Because the next thing is that the loop goes back around and I go back to line 14 and I get myself a new j because j got updated. So j is now pi on 6. And I've got to think to myself, what's the condition that gets checked? It's not this one, that's on the outer loop. It's this one, that's on the inner loop. Is pi on 6 less than 2 pi? Yes, it is. So I go back into that loop. And then that runs again, and I get 2 pi on 6. And that runs tick, and then 3 pi on 6, and tick. And the good thing about that, doing it this way, is I can see the pattern, that the j's are going to go all the way until they reach 2 pi, and then stop. So I don't have to fill in the rest. I can think to myself, what's the rest in there? And eventually I'll get to it ends up being 7 pi on 6. And I get an x over there in this column. So the next thing that happens after I get an x in that column is that's the end of the loop on line 14. So that we jump back around to the loop on line 12. And size gets updated to 80. And now I can check the condition that it's required on. Is 80 less than 8 times 40? Yes. So we go back into the loop. And guess what? The inner loop has size doesn't have anything to do with the inner loop. It does with the ellipse that gets drawn, but it doesn't with any of these conditions, so that I know that all of this is going to get repeated exactly the same again. And that helps. So I've seen the pattern now. I've seen the pattern that I'm going 40, 80, 120, so on and so forth. And I've seen the pattern that these are the same each time I go through. So this is the kind of table we like to draw to help us trace a loop, to know exactly how many times it's going to go round. Now that's especially tricky with nested loops, because how many times does this one go round? Right. Well, if I've worked out the pattern here, I know that this one goes round 13 times, because I can count that there's 13 of these in here if I'm careful about it. And on the outer loop, I realize it's going to go 40, 80, 120, through to, what does it go through to? 320, right? I mean, my maths is probably all wrong because there's too much going on in my head. The last one is 8 times 40, which is, yes, that's 320. And it's got a less than or equal to, so we actually go around 9 times. So we get 9 of these. And now I can, 9 of these. So now I can probably see how many times, because 9 of the outer ones, and every one of them has 13 of the inner ones. So the total number of times this goes round is 9 times 13, which I guess is 117, right? My maths is probably wrong again. So if someone asked me, what's the total number of times that line 15 gets executed? I think, unless I got my maths wrong, the answer here is 117. And I might have had to draw part of this table out to help me get the patterns just right, to calculate that it was 13 on the inner and 9 on the outer. And if I was a much more experienced programmer, I'd just go, yeah, 13 on the inner, 9 on the outer. But even an experienced programmer will get it and make that mistake a lot. Okay, so that was my demo of doing the tracing. I'm probably going to put together something else on the tracing as well. Just going to double check what resources we already have available. If there's something else already out there, I'll point you to that. But please hit me up with any questions now before we finish up. Anything? Yeah, so there's a heck of a lot of fun you can have here now with just expanding and expanding and expanding. So one thing I can do here is I can animate those inner circles instead of the outer circles. So let's say that instead of the gap being how much the outer circles were apart from each other, let's make the gap how far away the inner circles are from each other. And I'm going to start with 0.1 because we're dealing with radians here. And that means it needs to be a float. And you're going to complain, so we'll just chuck you down to a float 2 to make that complaint go away. And instead of the j going up by pi on 6 every time, the j is going to go up by a different amount on each frame. Yeah. Well, everything's going to expand now. Haha. Let's see what happens. Nothing. Oh, because I got rid of that line. So there's a lot of fun you can have experimenting with these things. Well, hey, didn't quite do what I wanted because we went way past 2 pi very quickly. So there's a perfect example actually of the kind of fun you can have experimenting with these things. You can think to yourself of an animation you'd like to try, and you can try it and find it not working. And then you can go back and trace through the program to see why it didn't work out your error, fix it, and move forward. So the problem I had there was that I very quickly got past 2 pi, which messed up the circles on the outer, but couldn't see anything when it was very small, which is what the big circles needed. So I really just need to take the big circles out of this entirely and need to make that grow a lot slower. So to take the big circles out of this entirely so they don't move, I don't start you at gap. I always start you at the same thing. And we just do this, so that you're not animating anymore, but the inner one's still animating. Well, hey, there we go. So the gap between them is growing each frame. Oh, I like that one. The 0 one's always there, right? Because it always starts at 0. I'm going to run that again. That was fun. I never get bored of silly little animations like this. Okay, yeah, experiment with them and then go back and trace. Experiment, make an error, go back and trace. That's your #1 way to learn how programming works. And it takes time, and it takes a certain kind of point of view. You've got to sit down and say to yourself, I'm going to make something that doesn't work. I'm going to spend an hour working out why it didn't work, and then I'm going to make it work, and it's going to be a funny little animation. There's not everyone in the world can convince themselves to do that. But if you want to learn how to program, you have to. And if you find that fun anyway, then you were born to program. All right. Well, I might leave it at that then. I shall do this again next week. And keep an eye. There's lots of interesting stuff on the textbook to help you learn this. I'll go away now.